Hi, and welcome to the channel. I am the Mad Computer Scientist. If you are new to the channel, please like, comment, and subscribe. If you find the videos useful, please share them out. If you would like to argue with others in the comments section, please do so. Today we're going to discuss the 3n+1 problem as it relates to math and, more importantly, to computer science. This video will go through the following things. We'll discuss the problem itself, we'll discuss the issue math has with it, we'll discuss the issue computer science have it, and there will be a few notes about the previous video where I think some people missed my intention and missed the most important part, or at least what I thought was the most important part of it. You are probably wondering what the 3n+1 problem is. It states that if you take any positive integer and do the following recursive function on it, you should eventually come up with a repeating sequence that goes 421, 421, 421, and goes on forever if you follow it that way. If you're going to write a program to calculate this, you'll usually stop as soon as it comes to 1, because you know as soon as it comes to 1 the first time, that sequence is going to keep repeating. And the function is for any positive integer 1 or greater. It should say greater than or equal to 1, but I did not type the symbol. If the number is even, you take the number and divide it by 2. If the number is odd, you multiply the number by 3 and divide it by 1. The first thing we're going to discuss is why this problem is unsolved in math, specifically in number theory, or how we know someone wasted a supercomputer's time on it. At the time I wrote this video, the highest known integer it holds true for that I could find is 2 to the 69th power. If you see a large number expressed as a power of 2, it is almost a certain sign that someone paid time to run the problem through a supercomputer perhaps multiple times. And one of the reasons to do this is to find an easy way to prove that the sequence does not hold true for numbers we haven't tested. The main reason it's unsolved is because no one has been able to prove it. If someone could prove it, and the proof were to pass peer review, they could win $1 million. At least the number theory problem. I do not know if this holds true for the computer science problem. Several attempts have been made, but so far none have succeeded. As I mentioned earlier, one of the ways you can disprove it is to find one number that we haven't already tried that does not come back to 421 as long as it meets the criteria of it being greater than or equal to 1. We should be able to prove it eventually, and some people recently have claimed to do it, but ultimately their attempt failed when other people looked at it more closely. This is one of those problems that if you're a new mathematician just starting your career, you will be told to avoid it because it will likely end your career and you will not have one. Now, the problem in number theory is not the same problem that computer scientists have with it, and the problem computer scientists have with it is interesting. Why it's unsolved in computer science. Basically, the issue is we can only predict how many times an integer will go through the sequence until it gets back to 1 when, not unless as it says, it's a power of 2. I first came across this program and problem in a computer science book trying to teach me Python that mentioned that yes, this was a famous on problem in math and in computer science. It mentioned vaguely that the problem in computer science was not the same as the problem in math, and it mentioned something about computer scientists not being sure whether it's an algorithm or not. I tried to find information about this for years and could not find it. Eventually, it occurred to me when, after I learned about runtime complexity, that the issue was you're not going to know what the runtime complexity is for a number you haven't ran through the algorithm yet. The problem in computer science has to do with the 3n+1 algorithm's runtime complexity. Computer scientists use runtime complexity to measure the speed of an algorithm, which is essentially how much processor time it takes up. It is broadly divided into polynomial time, or p time, and non-deterministic polynomial, or np time. I will post videos explaining this concept below. I also plan on doing a video on this concept after I do some research. The runtime complexity for the 3n+1 program is not known for a number that is not a power of 2 until the number itself is run through it. If the number is a power of 2, the runtime complexity is O log base 2 of n. I will also post notes for big O notation in the video below. And by the way, since this is a computer science channel, remember when I say log, I mean log base 2. You're probably asking, will this problem ever be solved? I'm sure it will eventually, but I have no intention of working on this problem. If I were interested in working in a theoretical computer science problem, I would probably try to solve the P versus NP problem, but I would have to currently understand how to prove a problem cannot be reduced to polynomial time than I currently do, and that would take a lot of work. Now, if you're only interested in the computer science portion that does not deal with basically middle school math, now would be a good time to click off the video. I also have a feeling it would be a good time to bring up my credentials at this point. I have a technical certificate in web development, an associate's in server administration, and a bachelor's in computer science, and I'm working on a master's in data science. Let's go over some points from the PEMDAS video. I expected this would generate a few arguments. There are plenty of videos that explain how the modern order of operations came about, as well as PEMDAS itself. The order I presented is correct regardless of what people tried to argue about it. The idea that there is a difference between implicit and explicit multiplication is a popular but incorrect notion. What I should have done, and this was my mistake here, is stress that the more important takeaway wasn't what the order of operations was, but the need to avoid writing problems in a way that is unclear in the first place. I should have started with that point, but it is towards the end of the video. With that being said, I thought we'd have some fun with math problems that people posted below. So here's some math fun from comments on the last video. They both come from Vibe77 guy. They were both variations on the famous viral problem that went around a few years ago. Unfortunately, he didn't realize that the answer to both the problems he presented is in fact 9, and any calculator or REPL program will give you the answer I gave. So 6 divided by 2 times 2 plus 1 in parentheses is indeed false, but 6 divided by 2 times 2 plus 1 in parentheses equals 9 is indeed true. But he didn't seem to realize that there is no difference between the divisor operator when it's the division symbol or the slash. It's a common mistake to assume the division sign means everything after the division sign should be evaluated before the division. But the truth is the division symbol has the same precedence as the slash. So how can we avoid this problem? Well, depending on how you want it interpreted, I've written both ways below. And the answers I've given are correct. Both of those statements are true. Note that I'm using a denominator instead of a division symbol. That way we can be clearer about the grouping and how we want it done. So in the first one, I have 6 over 2 times 1 plus 2 in parentheses. In the second one, I have 6 divided by 2 times 1 plus 2 in parentheses. The first one does equal 1, and the second one equals 9. See that doing it my way, we've avoided the confusion that occurred when we tried to do it his way. Another problem from the same user was unclear, and I tried to disambiguate it for him. And I did disambiguate several so he gets the answers he thought he was getting, but he tried to tell me I was wrong, and he did not work out the math on a calculator that does order of operations correctly, along with any REPL programs to confirm his results. I think what he meant to write was the problem I've written here, which is 3,000 over 4/3 pi times 3 minus 0.12 in parentheses. I have removed the units here, not because they're not important, but just to get the answer of 3, which is more important here, we need to have the problem correct in the first place. Now there is a value you can probably put in parentheses that will result in the slightly more than 3 than he wants. But remember, the best way to avoid arguments over PEMDAS in the first place is to write the problem so the person reading them knows what you mean. It is the responsibility of the person trying to communicate to make sure they're communicating as clearly as possible. And if anyone wants to work out the algebra to make the problem fit what he wants, the way I have it written, just do 4/3 pi x equals 1000 and you should come up with a value that gives him what he wants. All right, everyone. Thank you for watching the video. This one was a little bit longer. If you have any suggestions for other videos you would like me to cover, please write them below. If you have any math challenges or just fun math for me to try, write that below. And hey, if you have any cool programming projects, I'd love to see about those too.